class we have seen how to realize multiplexer based circuits, and we have seen that multiplexers they act as universal gate. So, you can realize any of these logic gates using multiplexers. However, the technique that we have seen for multiplexer based circuit realization is that we start with the truth table of the function and then we partition the truth table so in terms of the select variables. So, what I mean is that if I have got a 3 variable function say with the variables x, y and z, and I need to realize it in terms of a 2-to-1 or 2:1 multiplexer, then I am doing a partitioning where this I am doing a partitioning where these are all the combinations that I have. This is the truth table combination, and what we did is we if I have a 2-to-1 multiplexer here, then this if x is fed as the control input, then we divide this truth table into 2 parts. Okay. So, x equal to 0 and x equal to 1. For x equal to 0, we realize the function given by this, okay, and for x equal to 1, we realize the function. So, if this function is say f 1 and this function is say f 2, okay. So, we realize the two functions in f 1 and f 2, and this is the we put some combinational gates to realize this f 1 and f 2, and that gives the output. Now, the problem with this type of technique is that if the truth table is very large, that is the number of variables are a bit high, say more than say 5 or 6, then it is very cumbersome to write down the full truth table and do a partitioning in this way. A better approach for doing this is via the Shannon decomposition that we have seen. And in our last class, we have seen that Shannon decomposition around a single variable. So, if I have got a say you have got an n variable function f 1 f of x 1 x 2 up to x n. So, this can be decomposed around variable x I as x I bar into f with the function obtained by putting x I equal to 0, and rest of the variables remain as it is, plus x I into x 1 x 2 with x I equal to 1 x I plus 1 up to x n. So, this is a Shannon decomposition around a single variable. Now, this is suitable if we are thinking of realizing the circuit in terms of 2-to-1 multiplexers, because this the input x I will be fed as control input to this stage, and the function. So, we will be getting for 0 and 1 for 0 part. So, this will be realized by this function and 1 will be realized by this function. So, in short, so this is written as x I bar f x I bar plus x I and f x I. So, this is the notation. So, f x I bar means the function obtained from f by putting x I equal to 0, and f x I means the function obtained from f by putting x I equal to 1, and these functions f x I bar and f x I. So, they are of n minus 1 variables. Now, how can we generalize the method? So, if we are if we have got a 4:1 multiplexer instead of 2:1 multiplexer, if I have a 4:1 multiplexer, that is there are 2 select lines, okay, and we have got 4 input lines. So, this is for 0 0, this is for 0 1, this is for 1 0, and this is for 1 1, and these are my select lines say S 1 and S 0. So, if I apply say some variable, so x I here and x j there, x I to S 1 and x j to S naught, then for at this part I will look for the function obtained by putting f of x I equal to 1, say x I equal to 0 and x j equal to 0. Similarly, here I will look for the function obtained by putting f x I equal to 0 and x j equal to 1. Here I will look for the function f x I equal to 1, x j equal to 0, and here I will put the function f x I equal to 1 and x j equal to 1. That is, I am looking for a decomposition around two variables. So, if I write in terms of the similar expression that I have here, so we can say do it like this. So, we can do it like this, we can say f x 1 x 2 x n. So, if I am decomposing around the variables x i and x j, then this can be written as x I bar x j bar and f the function obtained by putting x I equal to 0, x j equal to 0, and rest of the variables they remain unaltered, plus x I bar x j f x 1 x 2 x I equal to 0, x j equal to 1 x n plus x I x j bar and f x 1 x 2 x I equal to 1 x j equal to 0 x n plus x I x j f obtained by putting x 1 x 2 x I equal to 1 x j equal to 1 x n. So, this way we can decompose a function around any number of variables, and accordingly we can get the functions to be sub functions to be realized in different inputs of the multiplexer. So, we can take an example. Suppose I have got a 4 variable function f a b c d equal to a b or a bar c d, fine. So, if we want to realize it using say 4:1 multiplexer, then we have to first select the choose the select variables. So, let us say that we will be using a b as the select variable. So, if we do that a b as the select variable, then I have to decompose around a b. So, I have to write it as a bar b bar f a bar b bar plus a bar b f a bar b plus a b bar f a b bar plus a b f a b, where by f a bar b bar I mean the function obtained from f by putting a equal to 0 and b equal to 0, and f a bar b means the function obtained from f by putting a equal to 0, b equal to 1, like that. So, if I just expand it, so this becomes a bar b bar into, so if I in the original function if I put a equal to 0, b equal to 0, so you get c d, fine, you get the function c d. Then a bar b into f a bar b, if I put a equal to 0 and b equal to 1. So, the first term vanishes, in the second term it becomes c d, sorry, the second term becomes c d again, because if I put a equal to 0, then this term vanishes and this becomes 1 and c d is there. So, this will also become c d plus a b bar into f a b bar. So, a b bar, so first term again vanishes and the second term a bar c d, since a equal to 1, so this term also vanishes. So, this is 0 plus a b into, so this is a b where this term evaluates to 1. So, this is 1. So, my final function becomes a bar b bar. So, if I say that okay, I have got a 4:1 multiplexer, then this is my f and a and b are fed as input to the select lines, then the data line input. So, this is for 0 0, this is for 0 1, this is 1 0 and this is 1 1, fine. So, here I have to put an AND gate with the inputs C and D, the input C and D, then 0 1. So, it also has got C D as input. So, you can directly feed it here also. Then A B bar is 0. So, you can put it as 0 here and A B into 1. So, you can put a 1 here. So, this gives me the realization in terms of 4:1 multiplexer. So, without going into truth table, so you can use this generalized Shannon expansion and go to the truth table go to the multiplexer based realization of the circuit. So, as the number of select inputs increase, so you have to the decomposition becomes a bit complex and lengthy. So, decomposition has to be for all the input permutations, all the input combinations of the select variables. Okay. So, with that we will be going to a new topic, which is demultiplexer. So, this demultiplexer is just the opposite of multiplexer. So, in a demultiplexer, so we have got it reverses the multiplexing function, takes data from one line and distributes them to a given number of output lines. So, to which output line the input will go, so that is determined by the select input. So, demultiplexer is also known as data distributor, as if the data is coming to the block and it is getting distributed to one of its outputs. A multiplexer on the other hand, it takes several inputs and transmits one of them to the output. So, multiplexer is just the demultiplexer is just the reverse of multiplexer, and symbolically also you remember that a multiplexer we are showing it like this. So, we are a multiplexer we are showing it like this. These are the data inputs. So, this is the output and so this is the select line. So, this is the way we are showing the multiplexer. Similarly, for a demultiplexer we will show it like this. The data input, there is a single data input and there are a number of data outputs. So, if I have got a single select line, then there will be 2 data outputs. So, if the select line is 0, then the output will be going there. If the select line is 1, then the input will be going to this output. If it is 0, it will go to the upper, the input will go to the upper output. If it is equal to 1, then it will go to the lower output. Now, a multiplexer, so a demultiplexer performs the reverse operation. It takes a single input and distributes it over several outputs. So, a general, so you can look at it as if there is a switch that goes from that can be get attached to one of the input positions. So, this to transfer the data input to that line. So, here this data input is coming and depending upon the select input. So, this switch will be set to one of these positions, accordingly the input will go to one of the output. So, this large arrow indicates one or more lines. So, it may be the case that instead of having a single line, so we have got a multiple lines. The select input code determines to which output the data input should be transmitted. So, it may so happen that instead of getting a single bit input, so from it is coming from some block that has got say 16 bit output, and the 16 bit output is connected to this demultiplexer as to the input of this demultiplexer to be transferred to one of many such 16 bit outputs. So, that way this arrows, so that may not represent a single line, they may multiple lines also. So, data input is transmitted to only one of the outputs as determined by the select input code. So, demultiplexer takes one input data source and selectively distributes it to one of n output channels, just like the multi-position switch. There is a multi-position switch, so it is doing it like that. So, as far as the logic level diagram is concerned, so this diagram shows a 1 line to 4 line demultiplexer or 1:4 demultiplexer. So, multiplexer we are writing like 4 line to 1 line or 4:1 multiplexer. For demultiplexer we will write as 1 line to 4 line or 1:4 demultiplexer. So, here we have got the select lines S0 and S1. So, if say S0 S1 both are 0 0, then what will happen? See, this is 0 and this is also 0. So, as a result all these 3 AND gate outputs, so they will be 0, fine. Only, so this D0, so it gets the input from this inverter and it also gets the other input also it gets from the output of this inverter. So, that way they are coming as 1 and this data input is coming. So, whatever be the data input that will pass on to D0, whereas D1, D2, D3 they will get zeros. Now, this so here you shall get a new notation. So, this bubble of the inverter, so it is shown before the inverter. So, that is also quite common. So, it does not matter. So, as if the input is inverted here and then buffered, or if the inverter is at the output, that means the input is buffered and then inverted. So, that way it is same. Previously also we have seen that these bubbles can be put before the gate or after the gate. So, you have to go by the logic and say what is the function realized. For example, if I have got a gate like this and here I have got bubbles, then I know that the function realized is AND of A bar B bar, AND of A bar B bar, which is nothing but A or B whole bar. So, that is a NOR gate. Okay. So, by applying De Morgan's theorem we can get it. So, this way we have to look into the schematic that we have, the logic symbols that we have, and interpret what is the corresponding signal. Typical timing diagram may be like this. So, this is the serial, so data input, suppose I have got a data input like this and this S0 S1, so they are doing some they are going like in this fashion. So, S0 is toggling every such boundaries, these dotted boundaries, and S1 is toggling every alternate such dotted boundary. So, initially both are 0. So, D0 will be getting the value of data in and others will all be 0 irrespective of the value of data in. After some time, so this S0 becomes 0 and S1 S0 becomes 1 and S1 remains 0. So, as a result D1 gets selected. So, D1 gets this data input at its output and others become, all others become 0. So, in this way you see that at any point of time only one of the outputs will get the value of the data in with it. So, others will be always, others are all 0. Now, in the, of course, you can say that it does not distinguish between a 0 which is coming from the data input and a 0 which is occurring due to non-selection of the particular output. So, we will see later that we can have some concept of tri-state buffer by which we can get rid of this situation and we can come to a new new logic level which is neither 0 nor 1. So, that we will see later. So, one line to 8 line demultiplexer. So, that previously what we have seen is a 2 to 4 demultiplexer, to 1 line to 4 line demultiplexer. So, this is 1 line to 8 line demultiplexer. So, naturally I need 3 select lines S0, S1 and S2, and then we have got a number of AND gates and these symbols are ANDed, like say this is this output is 1. So, here I do not have any data input to be transferred. So, we only say that if it is which one is, so this sorry the data input is there and data input is transferred to O0 if this S0, S1, S2 all are zeros. In that case the data input goes there. If it is equal to S0, S1, S0 is 1 and S1, S2 are zeros, then this O1 will get the value of data input. So, this way this logic circuitry has been made. Accordingly, in the truth table you can see that this I can the input I can pass can come to only one of the outputs O0 to O7 at any point of time depending upon the select lines S0, S1, S2. Next, we will be looking into another fundamental concept which is known as buffer. So, what happens is that whenever we are transmitting signals over long distance, okay. So, due to this noise and this RC drop of the line, so the voltage level of the signal drops, okay. So, maybe you have transmitted a logic high, but due to the length of the wire at the other end when you measure, so you do not get a strong logic high. So, you get some intermediary value, or in the worst case it may even become a logic low level. So, what is required is that we should do some amplification of the signal. So, signal voltage level has to be restored to the proper values. So, if I have a line like this, so if I have a line like this, so what I mean, so at this point I am sending some value signal S. At this point when I am measuring S, I find that it is not that strong. So, what is done in between, we put some buffer like this. Okay, this buffer as it is shown here. So, this buffer will amplify the signal. So, it does not, so it is basically a true value transfer. So, whatever is coming as input will go to the output, provided this enable line is equal to 1. If this enable is equal to 1, then in output equal to input. So, it does not do any other logic change to the signal in. So, these are also known as 3 state buffers, because when this, what happens when enable equal to 0? When enable equal to 1, then I have said that output gets input. So, what if output enable line is equal to 0? So, this type of buffers where we have got an enable line, so they have got 3 output states 0, 1 and Z. So, Z is known as the high impedance state or open circuit state. So, as if the circuit is open, okay, it is not connected to any voltage source. So, enable equal to 0, output equal to Z, which is equivalent to the open circuit, and enable equal to 1, output is equal to in, that is the regular buffer operation that will occur there. So, enable equal to if we do not want the output to get the value of input, so we can put enable equal to 0, and that will stop the output getting the value of input. Now, there are many such 3 state buffer configurations. So, I can have this buffer with enable high. Enable high means when this enable equal to 1, then only this output will get the value input. Sometimes we have got a, so this is a buffer, so this is a 3 state inverter. So, this is a basic inverter logic, but before that we have got, so there is an enable line also. So, if the enable is high, then only this circuit will act as an inverter, otherwise this output will be tri-stated. So, output will get the value Z. So, this Z is also known as the tri-state. Okay. Z that I am talking about, so that is also called the tri-state. There are several names. One name we have already seen, the high impedance state. The high impedance state or the tri-state state. So, like that we have got several names for this. Now, this so we have got this thing, we have got this enable, and if enable is 1, so this is basically an inverter with some enable line. This enable can be, the enable itself may be an inverted enable, that is this buffer will get the value of output will get the value of in, provided this enable line is equal to 0. If enable line is low, then output gets the value of input. And if this enable line is, similarly I can have an inverter where the enable line itself is low. So, this is we have got this enable equal to 0, then only this circuit acts as an inverter. So, that is possible. So, we can have various combinations of this buffer. Next, we look into let us see like why this is necessary. So, this is necessary because many times what happens is that we have got different logic blocks, they are giving me some sources. So, this is say block 1, whatever it is. So, this is block 1, this is block 2. So, they are all logic blocks computing some logic operation, and then we need to give this output of both the blocks to block B3. So, block B3, okay. So, this output should be this input should be coming from the output of B1 or B2, but at any point of time only one of them has to be connected, and sometimes this input may not be connected also. So, what I mean is that sometimes this B3 gets the value from B1 or B2, or it may be that it is not connected at all. Now, we will see later that if I do it like this, if I connect it in this fashion. So, what I really want is something like this, that these are the outputs from B1 and B2 and this is going there to B3. Now, this type of connection is difficult because what may happen is that there may be conflict in the outputs of B1 and B2, and in that case, so what is the voltage level at this point? So, this becomes a question, fine. So, to avoid that situation, so we can use the tri-state gates, the high impedance gate. So, what we do is we put buffer here, sorry. So, let us take a new page. So, we take we have got this B1 and output of it is put to a buffer, and we have got a block B2, and this output of B2 passes through another buffer, and these two are now connected, and that goes to the block B3, fine. Now, this enable line, so they will be, so this is say enable 1 and this is enable 2. So, if enable 1, so this B1 output will be coming to the input of B3 if enable 1 is high, and likewise B2 output will come if enable 2 is high. Now, you see that if enable 1 and enable 2 they are not activated simultaneously, then I do not have any problem. So, this B1 output is never getting connected shorted to B2 output. Okay. So, that will not happen. So, this way we can use this tri-state logic for realizing this type of connections, where multiple outputs from different blocks they may be connected to a common input of another block.